and part of the fellowship is learning how to teach. And so, although I've taught many times before, it's usually in groups of 30 or 40 students, and this is a lot larger. So I'd be lying if I said I wasn't a little bit nervous. So if I trip over my words, or better yet, if I trip over myself, just help me up and encourage me a little bit, and everything will be just fine. Since I am going to be teaching this week, I think it's only fair that I'm also offering some office hours. I want you guys to be able to come and ask questions if you have any. So if any of you have been to Dr. Dixon's office before, you know there's that little side office room kind of next to her office. I'm going to sit there on Tuesday and Thursday this week, and since she's normally having an open door policy from like 9 to 3-ish, in case you can't meet her during the day, I decided to have office hours from like 3:30 to 5:30 on Tuesday and Thursday. So we just jot that down. So this Tuesday and this Thursday. 3:30 to 5:30. I'm going to be sitting in the office just next to her office. And if definitely if you have any questions, because there's so much material to cover throughout this whole week, starting with today, I may not be able to take as many questions. So if you ask a question and I can't answer it right away, definitely come to my office hours, and you're free to talk to Dr. Dixon as well. And of course, Ken has discussion this week as normal. Let's see. Okay, so I have office hours there. And this week, in case you haven't already figured it out, we're going to talk about electrophilic aromatic substitution. This whole entire week. It's like a brand new tool that you guys haven't learned about before. But first, if you remember from last week, Dr. Dixon was talking about aromaticity. She introduced what is an aromatic compound, right? There's the 4 rules of what makes something aromatic. And so I want to start out today by just, instead of having a quicker question, just take, 5 seconds and tell me whether this compound is aromatic or not. Yeah, so who says it's aromatic? And who says it's not aromatic? Let me try that again. Who says it's aromatic? Not aromatic. So it actually is going to be aromatic in this case. The reason why it's aromatic is that even though we have this pair of electrons here, it's not going to be part of the pi system. It's an sp2 pair of electrons, but it's outside of the pi system between this electron and these pair of electrons, these pair of electrons, and these pairs. And if you remember, one of the rules for aromaticity is it has to meet that 4n plus 2 requirement. That's Hughes rule. And the n is any integer, and 4n plus 2 is the number of electrons, pi electrons. So I have 1, 2, 3, 4, 5, 6. And so if you have 4n plus 2, and if n is 1, then you have 6. So that having 6 electrons in a pi system meets the requirement of an aromatic compound. Does anybody have any questions about that? Is it okay? Yeah.
I have a question about that. Shouldn't it be on the other half?
You're talking about over here? Good. So she's pointed out a very important detail, which hopefully I would have figured out pretty quickly. So that was the bridging example. Now I'm going to talk about electrophilic aromatic substitution. And correct your notes if you wrote, I put 2 double bonds in here. So, when Dr. Dixon was talking on Friday, she mentioned about the stability of aromatic compounds. And in order for you to be able to do reactions with aromatic compounds, you need to, it needs to be a really good electrophile. For example, in this case, the aromatic compound, and for the whole week in this whole unit, the benzene ring for the aromatic compound is going to be the nucleophile, always. But this nucleophile is not going to react with just any electrophile. It has to be a very, very strong electrophile. For example, if you guys remember back from Organic 1, if you take something like cyclohexene, in BR2, this one I know you guys could do in your sleep, right? It's a piece of cake. You get trans dibromo cyclohexene, right? take this same Br2 and instead if you mix it with benzene instead of cyclohexene, and you mix with Br2, you're going to get no reaction. Nothing's going to happen unless we add some sort of catalyst, in this case an acid catalyst, to convert this weak electrophile into a strong nucleophile. And that's really what I'm going to focus on over the next 40 minutes, is how to convert some of the okay electrophiles into strong ones so that it will undergo electrophilic aromatic substitution. Yes?
Sorry, going back to your first question, isn't the third rule for all of them to be sp2 hybridized? And that second nitrogen is sp3 hybridized?
This one, where's Dr. Dixon? There she is. It's still okay, right?
Yeah, that's an sp2 hybridized nitrogen right there that has an electron pair on it for neutrality. The electron pair on that nitrogen is going to get that nitrogen. Yep, that one. It's part of the pi system. So that nitrogen is sp2. It has a hydrogen, a carbon, and a carbon, right, as its attachments in sp2. The electron pair is part of the pi system. The nitrogen with a double bond is sp2, maintained that way because the electron pair is part of the sp2 system.
Is
I'll
that
come back more after. We're welcome to do that.
yeah.
But I was just wondering if resonance happened, it wouldn't become linear SP, the carbon on the left or on the right, and wouldn't linear not be okay enough?
It should still maintain linearity because if you did move this over here, and maybe
Okay.
you should be able to move this, and then you should be able to move those around, right? Okay, yeah, it will be okay. I'm gonna erase this before it gets too much. If you want to come and talk to me about it, I'll hash it all out during office hours. And actually, on that note, I want to take 1 second and just give you a brief overview of what we're going to do the entire week. So today, you already know we're talking about electrophilic aromatic substitution. So it's for Monday. Monday is EAS reactions. And Wednesday, we're going to do more of the EAS reactions, except this time we're going to do them of derivatives. Because as you're going to find out, once you have your electrophile added onto the benzene ring, there's going to be cases where, what if you want to use this molecule and you want to do other reactions? Or what if you want to add other things onto it? It turns out that whatever electrophile you put on here can have some directing effects where it can kind of coax whether the next electrophile is going to add in this position, which would be ortho, in this position, or this one, which would be meta, or down here, which would be para. Not only can it have an effect on the direction of how the next electrophile adds, but it can also have something to say about whether that reaction is going to go faster, or the fact that this electrophile is here, it'll make a reaction go slower. So that's kind of a lot, but that's what we're going to talk about on Wednesday. Today we're just going to talk about how to get these here. Wednesday we're going to talk about how to add on other ones and whether those will be faster or slower, respectively. And then Friday, of course, you guys can't get away with learning about aromatic rings and not talk about the spectroscopy, right? The characterization. So Friday we're going to go over nomenclature. Probably you can't read that. Nomenclature as well as characterization, which includes spectroscopy, NMR, IR, UV vis. That'll be for Friday. And on that note, starting out on Wednesday, I'm going to ask a quicker question right off the bat on Wednesday. It'll have 2 questions. One will be a review question from today, and then on Wednesday, I need you to get ahead a little bit to kind of have an idea about directing effects or what exactly like ortho, meta, and para means. So look that up in your book if you don't already know. It's going to be something like that, but quicker question on Wednesday. And I'll do the same exact thing on Friday as well, a review question and a read ahead question. Just going to throw that out there. Okay, so that's for the week. Today with the electrophilic aromatic substitution, there are 5 general reactions that I'm going to go over, and I'll write those down here, and then I'll go through each one of them. ends here with the ations. They're all going to be something, something ation. A sulfonation, alkylation, and acylation. And I want to point out that the alkylation and the acylation, they're actually formally referred to as Friedel-Crafts alkylation and Friedel-Crafts acylation. Hopefully you can read that okay. It's named Friedel-Crafts alkylation and acylation because those are the two scientists, Friedel and Crafts, that worked together and discovered these two types of reactions with the aromatic benzene compound. So I like to just call them these five, but keep in mind that it's actually Friedel-Crafts acylation, Friedel-Crafts alkylation. And as you could imagine, all I'm going to do here is we're going to halogenation. Our electrophile is going to be a halogen. So over for our product, you're going to have a Br, a Cl, or an iodo product. And for nitration, we're just going to add a nitro group. You guys know NO2. Sulfonation is going to be SO3. And alkylation could be any alkyl group. So whether it's a methyl, an ethyl, propyl, anything you want to come up with, I'll leave it at R. Then you alkylate, so you add on those carbons. Or acylation, you add on an acyl group. And I'll talk about what an acyl group is in just a minute if you don't already know. But first I'll get started with the halogenation. So even though this has no reaction, if we add a little bit of acid catalyst in the form of iron tribromide, then we can convert this weak nucleophile into a strong enough nucleophile that the benzene ring is now going to want to donate its electrons over, which will allow the electrophilic aromatic substitution reaction to occur. So first, we need to generate this into a strong electrophile. That was pretty tough, right? I'm just going to put those together. So essentially what I've done is take the Br2 and the iron tribromide, and I just complex them together. And when this happens, you end up with a formal positive charge here and a formal negative charge over here. And now we've converted this from a weak or okay nucleophile into a very strong one, which is going to allow the electrophilic aromatic substitution to occur. Yeah, so let me reiterate that it has to be strong because remember that the aromatic or the benzene ring, being aromatic, it's more stable. One second. And it's going to take something really strong in order for it to even temporarily break its aromaticity. And so that's why we need a strong one. Yeah.
Just to double check, is that supposed to be FeBr3 or is it supposed to be FeBr3 on the left side? Which one? Is there a mixture? Okay. Thank you.
Thank you. Yeah. Good catch. Okay, so now I have my strong electrophile. I'll start the reaction over again. Here's the benzene ring, which you guys will get very good at writing this whole week because that's all we're going to do. Every time we start a nucleophile, benzene ring, nucleophile, benzene ring. So I'll put N for nucleophile. I'll write my electrophile over here, which I've just made. What we can have is a pair of electrons, any pair of pi pair in the benzene ring. I'm just going to pick this one because it's closer, but ideally you could choose any of these pi pairs to donate its electrons over here to this one, so that now the pair of electrons between these two bromines can add over here, alleviating the positive charge in that bromine. So the left side of the benzene stays the same, and you'll see that pretty much the whole rest of the day. Everything stays the same over here. I haven't done anything. All I've done is add on the bromine. I haven't even gotten rid of the hydrogen yet. Everything's right. You still have 6 hydrogens here. Hydrogen's still there. All I did was add the bromine. And of course, because I took the pi pair here between this carbon and this carbon is now electron efficient, so we have a carbocation, which I've drawn here. Yes?
Does this go through the brominium ring, the three-membered ring?
No.
No.
Not like the other bromine reactions with the alkenes. There's a good question like that. Cyclohexene I just had on the board, that goes through a three-membered ring. This one does not. It's just like it is here. Right, so this is like a temporary break in aromaticity, right? So it had to be a strong electrophile, but now that it has formed, there has to be something a little more stable about it, right? And even though it's a secondary carbocation, do you remember like with the allyl and with the benzylic, how you can have resonance structures, which is why I've drawn these over here. So if you just replace the E here with the Br, you have the same exact thing. And so the pair of electrons here can move over, so you shift the carbocation from there to here. And do the same thing one more time, so the carbocation can go up here, and it can basically just go around the ring. So it's resonance stabilized. So even though it's a secondary carbocation, it's more stable than a normal secondary carbocation because of the resonance stabilization. And this is really important that you will be able to draw it. So maybe one of the exam questions, which I'm going to be helping to write for your next unit, is maybe instead of having you draw the whole mechanism, I might just say, draw the resonance structures for like this. Show me the resonance structures. And you should be able to do that, in 5 seconds and feel comfortable with drawing the resonance structures. Similarly, I might also ask you, instead of drawing out the whole entire mechanism, I might just say for something, just generate the strong electrophile. Take it from a weak one to a strong electrophile. Show me how to do that. I might not ask you to do the whole entire reaction. So just keep that in mind. Is everyone okay so far? Yes.
Why doesn't the nucleophile attack the bromine with the positive, with the normal charge on it?
I also forgot that this is going to be a minus charge here, just so you guys know. Okay, so I don't know exactly how to answer that, actually, Dr. Dixon. No, okay. Oh, yeah, I have a question for you.
Having a little bit of a hard time. So if you continue with your arrow pushing with the intermediate there, that bond between the two BRs is actually going to be donated back to the BR with a positive charge. So what it leaves is a BR with 3 electron pairs and a positive charge.
Over
So
here.
draw an arrow that's between the two bonds of BR, going back to BR with a positive charge. There just needs to be an arrow there. And then it'll leave behind a full BR with a positive charge. 3 electron pairs and a full positive charge. Yep. And that's actually what gets captured. Oh, why does it attack that? That BR, that's actually a really good question. Okay. Very good question. And the answer to that question is different. The answer to that question is the BR in the intermediate is Ron doesn't have a positive charge because it wants a bond. He has a positive charge because it gave away an electron. Very big difference. Now, when you see the resultant arrow pushing and you get the BR with 3 electron pairs, that BR now wants a bond, right? Because it only has 3 electron pairs around it. So, that's very like. So, if you come around and show the resultant arrow pushing, you get. I won't sit so far away next time, I promise. Sorry. This is like the Price is Right, though, isn't it? Come on down! All right, I've always wanted to do that. I know, I should be like, yeah, it's not that fun. All right. So, what you get is this guy here, and this guy is saying, I want a bond. I have 3 electron pairs, I want a 4th, right? This one has 2 electron pairs and 2 bonds, right? It doesn't want another bond or it'll go beyond the octet. This one is desperate, right? So once you go through this, you get this guy, and this is the one that's getting captured. Okay?
What she said.
I know! I want a prize! Yes! All right! It's not a new car, though, is it?
Next time.
Okay.
Wednesday. If the same thing happens on Wednesday. Okay, does that answer your question? Okay? Yeah, sorry. Sorry for that. Okay, so that should make more sense. And so let me reiterate that the book can have it one or two ways. So the book leaves it like but it actually can also be drawn this way. So you have FeBr4 minus and Br plus, and that's where that's coming in. So either way you want to draw it, this way or this way, you would get credit either way you drew it. There wouldn't be any penalty. It's the same. Okay, so now that we have the resonance stabilized form over here, carbocation, the last thing we have to do is restore the aromaticity and finish the substitution. So we've added on our new thing. Now we need to take off the hydrogen, which would also restore our aromaticity simultaneously. So still swimming around in solution now is the FeBr4 minus. And essentially that will just come right over here and pick up the hydrogen, which will take the pair of electrons between the carbon and the hydrogen and can add back over into the benzene ring. So you've restored aromaticity, and now you've completed the electrophilic substitution. Yeah, and be careful. Somebody in the whole of organic students are going to think that you want to take this negative charge and go to the positive charge, right? You're going to be really nervous on the exam, and you see a negative charge and a positive charge, you're going to want to drive it right over there. Don't do that. Put like a giant X in your notes. That doesn't happen because if that were the case, what would your product look like? Right? So you have some strange complex over here that doesn't look right to have on a benzene ring or on a cyclic ring. Br, you still have the H, but what about this compound now? Is it aromatic any longer? Yeah, not aromatic anymore. That's why this is not going to attack the carbocation over here. It will lose the aromaticity permanently, and that's just not going to happen for benzene. It wants to maintain that stability. This would be a huge loss in stability here. So this never happens. Always the conjugate base of the Lewis acid is going to come over and pick up the hydrogen that's attached to where you're doing the electrophilic aromatic substitution. Is that okay? So that's pretty much it. That's the whole mechanism. I'm going to do the same exact mechanism for nitration, for sulfonation, alkylation, acylation. They're all the same. I'm just using different Lewis acids and different electrophiles. But the whole steps, they're all the same. So instead of doing the whole mechanism, what I'm going to do is show you how to generate the electrophile, because that's the important part we end up doing on an exam. This is important too, but I think getting the electrophile is a little more tricky.
Zoning out? Are you zoning out?
Figure them out over here.
Nice catch.
Yes. So the reason why I added the Lewis, he was asking why we added this in here. And the only reason why we added this Lewis acid was so that it would convert this from an okay electrophile to a very strong electrophile. Because we know that it would make this complexation and start drawing that electron density away from here, which would then make the pair of electrons donate back over to alleviate that positive charge. And he did that so fast he didn't realize he gave himself a positive charge. And then since this is very, very strong, this immediately comes over and saves the day and picks it up. Like in so to speak. Yeah. So the next one, nitration. Can you guys see the board if I write all the way over here? So we start out with nitric acid. Not that. So you have nitric acid and sulfuric acid. That's going to be our Lewis, or that's going to be our acid catalyst in this case. So nitric acid and sulfuric acid still return off the benzene ring. But this is not a very strong electrophile. So as you see throughout the whole class today, it's making a strong electrophile. And if you know, if you remember, nitric acid is written this way. That's what nitric acid looks like. So if you see this OH group here, if we could just get one more hydrogen on there, it would look like pseudo water, and water is an excellent leaving group. So then this could leave, and that would leave me my nitro group. That would be my strong electrophile. That's what I that'll give me pseudo water. I think I've run out of wood space. I'm gonna have to shoot it over here. Hopefully you have it written in your notes, so you have a little more room. So I'm just gonna shift over, and the product for the nitric acid over with sulfuric acid is going to be pseudo water. And now it's the same exact thing here, except I'm just not going to have a hydrogen. So instead of H2SO4, it's just going to be HSO4 minus, because I put the pair of electrons from that bond over. So we're almost there. Water is an excellent leaving group. It's just going to leave and take its electrons with it. So then I have neutral water. Plus now my very strong electrophile. And I still have the HSO4 minus. Right. So now I've generated my electrophile for that. Yes.
How come the nitrogen has a positive charge of this 5 bond?
Looks like I have 5 bonds on it, right? Yeah. Do you guys see what I've done?
Right.
Yeah, let's say, I'll call it, I was tricking you guys. I put 5 bonds on nitrogen. Don't do that. Let me fix it. Thank you. Yeah, so there's still a positive charge. It should be 4 bonds on nitrogen, but not with, yeah, much better. Yeah, thank you for correcting me. So here's my electrophile. The same exact thing is going to happen. Just put NO2 plus in place of the E over here, and you have the same exact thing. You get the NO2 over here. You're going to have the resonance stabilized structures. Then that base, in this case, or the conjugate base, as you say, H2SO4 minus, or the water, can come over and pick up that hydrogen, right? So all I have to do to restore the aromaticity is pick up a hydrogen, and that pair of electrons from the hydrogen and carbon can then donate its electrons back into the ring, restores aromaticity, and now the reaction is complete. Does that make sense, or should I go through the mechanism? Mechanism? I'll go through the mechanism. Either the water or the sulfuric acid. So now I'm going to draw out the reaction. Okay. Okay, if you start out with the benzene ring, I'm going to start from the very beginning with nitrogens. You have the benzene ring, that's your nucleophile. You have HNO3, and you mix that with some concentrated sulfuric acid, which is H2SO4, and the final product is going to be the benzene ring with a nitro group, which is called nitrobenzene. And I'll go over the nomenclature on Wednesday, but for the record, it's nitrobenzene. So the mechanism from getting from here over to here, we did half of it already, right? By generating the strong electrophile from the weak one. The stuff I just erased over here. And then I have the pseudo water. Water's just going to leave. Then I have water, my very strong electrophile, and the conjugate base of H2SO4. This is what I'm going to use to do that reaction. So now that that's the whole reaction, the mechanism looks like this. Pair of electrons from the benzene ring, any of the pi pair, is going to pick up that nitro group. And because I've taken the pair of electrons here, now this carbon's electron deficient, so it has a carbocation. I haven't done anything with the hydrogen yet. all I've done is add on the nitro group. So now we're almost there. Now we're to the point where on the left-hand side of the board, you could draw these three resonance structures. So that secondary carbocation is resonance stabilized. From that point, all you have to do is get rid of this hydrogen and have the pair of electrons between the carbon and the hydrogen go back into the ring, so it restores aromaticity and you've completed the substitution. So we're almost there. And to do this, I could use either the water or I could use H2SO4 minus. Either one is just fine. I'll take the HSO4 minus. That's going to come over, pick up the proton, the pair of electrons between the carbon and the hydrogen. It's going to go back into the ring. That restores the aromaticity, and now the reaction is complete. Yeah. Does that make more sense? Is that helpful? Do you guys have any questions? Yeah.
Don't you at a certain step, like, just regenerate the sulfuric acid?
Yeah, so that's an excellent point. So in the solution, you have a very concentrated sulfuric acid, H2SO4. So a lot of it is H2SO4. Some of it is H2O. Some of it is H3O plus, and some of it is HSO4 minus. You have all of those components around, which is why it doesn't matter if you have HSO4 minus come over and pluck off this hydrogen, or if you have water come over, they can both act as the base here, mixed in with that strong sulfuric acid. Because you also have nitric acid in the solution as well. It's just disappearing as the reaction proceeds. But the other ones are just regenerating. Good question. Any other questions? You guys see how I did the same exact mechanism actually? It was kind of all over the board. But it's the same exact mechanism for halogenation that I did for nitration. I just generated the strong electrophile. Then I took over here, where did I? Yeah, over here. I picked up the strong electrophile. Now I've temporarily broken the aromaticity, and I have resonance stabilization of that secondary carbocation that I've drawn over there. And then a conjugate base comes over, picks off the hydrogen. That's all that happens in halogenation, nitration, sulfonation, alkylation, acylation. So I've done two. Now I will go on to sulfonation. Sulfonation. And the first thing we have to do is generate a strong electrophile, which is actually going to be sulfur trioxide. So we have to form, well, we're going to form HSO3 plus. So we're going to react. Okay, so the first thing we have to do is generate our strong electrophile. And even though this is written as sulfuric acid and sulfuric acid, I'm going to rewrite it in a way that is the same exact thing as nitration, where I make that pseudo water. And if I make pseudo water, then water can leave, and then I'll have my strong electrophile.
Isn't benzosulfonic acid more acidic than sulfuric acid?
Is it what?
Isn't the pK of benzosulfonic acid like
Very,
more negative?
very strong, yeah. So she made a good point. So she's pointing out that what you're going to form is even a stronger acid, and always react from stronger to weaker acid. In this case, it's stronger. So what I should note in the reaction is the only way this is going to happen is if I apply some heat, and these are extremely concentrated. So not only is it concentrated enough to burn a hole in the floor, but you're also going to heat it. Sounds like a dangerous reaction, but somebody did it. Yeah, so that's how the reaction is able to proceed. So under these conditions, I can take the same thing I did for nitration, a pair of electrons, and bring it over. And then we draw out that hydrogen. The pair of electrons can move on to the oxygen. So that gives me my pseudo water. And the H now SO4 minus. And so the water can leave. We're almost there with forming our strong electrophile. All I have to do now is take the pair of electrons here, give them to water, so it'll be neutral, and I have my electrophile. And I still have the same HSO4 minus. Great. So now I can take this, and now I can do that electrophilic aromatic substitution reaction. That can take the pair of electrons from the benzene ring, and come over here, pick that up. And now I've generated the carbocation and the resonance stabilized intermediate. I'm just not that tall, so I'm gonna have to scoot down. Sorry, guys. So this is just gonna be here. Forget about that. Okay, does everyone see how I got this? Okay, so the same thing as the other two mechanisms. Now all I have to do is come over and pluck off that hydrogen, so I can take the pair of electrons here, put it back into the ring, and then the EAS reaction is complete. So to do that, I can either use, again, the water, or I can use the HSO4 minus. Either one is fine, and you can use either one on exam or homework. So I will use the HSO4 minus. Come over here, pick up that proton, pair of electrons goes onto the ring, and now the reaction is complete. Do you guys have any questions? There's one thing I want to point out about this reaction that's different from the other five. This reaction is actually reversible. So this whole time I've drawn reaction arrows that go in one direction, but actually you should note that it's in equilibrium and it can reverse and go the other way. So in your book, even when it first shows the first reaction, it also shows just one arrow. But actually, if you read the details of the book, you'll see that the reaction is actually in equilibrium. So really what we should do is always draw the arrows to show that it's in equilibrium. It's like fish hook. Remember the fish hook this way, fish hook that way. Still with heat and concentrated. And then in each of these steps here, so that this is also equilibrium. And this is also equilibrium. Yeah, and the equilibrium arrows aren't exactly equal, but you should know that it can reverse. So if you got, a multiple choice question on your exam that said which of the EAS Alright, so the last one I'm going to talk about is acylation. And so an acyl group is just another functional group. Kind of like you have carboxylic acid, right? It's a carbonyl. If I put an OH here, that's a carboxylic acid. If I put an OR here, that's an ester. If I put an N here, that's an amide. You guys know all that already. So if I put, well, this soap, you just consider this group by itself without anything on it at all. This is referred to as an acyl group. And that's spelled ACYL. So this is an acyl functional group. And one of the most common acyl groups that we'll see, at least for these reactions, is going to be an acyl chloride. In which case, it's just the acyl with the chloride attached. And so as you can imagine from the other mechanisms we've drawn, it's going to be the same exact thing, except for now, I'm adding this into the benzene ring, as opposed to adding the nitro group or the alkyl group or the halogen. So let's do that. I'm just going to leave it as R, but it could be CH3, ethyl, propyl, doesn't matter. And again, so the same way in all 5 of the reactions, I'm going to use some sort of an acid catalyst. In this case, it's going to be the Lewis acid, AlCl3. And aluminum trichloride is basically going to do the exact same thing as a halogenation reaction. Remember the iron tribromide? This is now aluminum trichloride. So iron tribromide, aluminum trichloride. It's going to do the same exact thing. This is going to make a complex together. Then it's going to leave this with a, it's going to make this very electrophilic, and the ring is going to pick it up. You'll have your product. Yeah, so that's the reaction for here. In order to generate this from a weaker or an okay electrophile to a strong one, you just complex them together. So the same way before, where you had the iron tribromide and there was that positive charge on the bromine. So now what's going to happen is this pair of electrons is going to come over here to alleviate that positive charge. You'll have the acyl group. And now you'll have the AlCl4 minus. And this is what the benzene ring is going to come over and pick up. Give me that. Or actually what it gives me